Thanks everyone for joining us today. Today we have Mansi as our guest speaker. Mansi is a master's student in computer science at UMass Amherst, where she's advised by Professor Bruno at Autonomous Learning Lab. Her research focuses on lifelong reinforcement learning, studying how RL agents can continually adapt under non-stationarity. Uh, the Mansi is going to present her work that is published at COLAS 2025 as a poster and accepted at AMAS 2026 oral. Um, so, Mansi, the floor is all yours. You can get started.
All right. Hi, everyone. Good morning. As Rahul introduced me, I'm Mansi, and I'll be presenting AltNet, our solution to addressing the plasticity stability dilemma in reinforcement learning. At a very high level, this talk is about a simple contrast in humans and artificial intelligence. So, humans or biological intelligence continues learning throughout its life, whereas artificial agents are trained once, frozen before they're deployed. So, the gap is at the heart of continual learning or lifelong learning. And in this talk, I'll explain what the plasticity stability dilemma is, why it matters, and our approach to addressing it. This work was recently accepted at AMAS, the Conference on Autonomous Agents and Multi-Agent Systems. It's been carried out at the Autonomous Learning Lab at University of Massachusetts Amherst. It's in collaboration with John Racebeck, a PhD student at UMass, and it's advised by Professor Bruno Castro da Silva. Okay, so continual learning is asking a simple and ambitious question. Can we build AI systems that keep learning after deployment, continue accumulating knowledge over their lifetime, just the way we do? Um, when we think about why continual learning is hard, there are two challenges or two distinct failure modes. One of them is catastrophic forgetting, where learning something new overrides what was previously learned. And the second is plasticity loss, where the network gradually loses its ability to learn anything new at all. And a lifelong learner or a lifelong learning AI agent needs to be able to do both, remember the past as well as have the capability to learn the future. Let's start with taking a deeper look at catastrophic forgetting. This problem has been the dominant focus in continual learning literature for almost 30 years. Prior work that has been designed around the all the prior work has been designed around the assumption that network is still capable of learning, and the real challenge is simply preserving the past knowledge. Uh, a lot of solutions that have fallen under catastrophic forgetting in order to address it. Some of them have been regularization based methods. These approaches are trying to protect important parameters by penalizing change to weights that matter for previous tasks. The main idea is learn new things, but be careful not to move any important weights too much. The second family of solutions are replay based methods. So instead of only protecting weights, these methods revisit the past directly by storing or generating old experiences and mixing them with new data during training. So the model keeps seeing previous tasks while learning the new ones. A third family is the architectural models. These methods reduce interference by allocating separate parameters or separate modules for different tasks. So, instead of forcing one shared network to do everything, they carve out specialized parts of the model over time. Now, all these approaches are really valuable, and they've helped address catastrophic forgetting. But the point is that these solutions designed to prevent catastrophic forgetting sometimes reduce plasticity. Let's see how. So, uh, for the first part, regularization. If we keep penalizing changes to weights that were important before, then the network becomes increasingly rigid. So while that is helping retention, it is reducing the network's flexibility, which is needed to adapt to new data. The second family, replay. If you keep replaying past tasks or past information, you might be creating kind of interference to learn new tasks. The network might be forced to maintain representations that don't align with what the current objective needs. So replay can stabilize learning, but it can anchor the network too strongly to the past. And then architectural approaches introduce a very different kind of rigidity. One is that as the model grows over time, and as the model grows, older modules are frozen. So earlier representations may not benefit from later learning. And the cost of stability here is fragmentation. This gives rise to what we call the plasticity stability dilemma. If we move too far in the direction of stability by somehow freezing the parameters or heavily constraining the updates, we protect old knowledge, but we are losing adaptability. We are making the network more rigid. And if we move too far in the direction of plasticity, which we'll see in the future slides, we are able to restore learnability, but we risk instability. The challenge is not choosing one or the other, it is balancing them, because a lifelong learner or a continual learning system requires both these capabilities. So now let's take a deeper look into plasticity loss. Now, when do we say a network or an agent has lost plasticity? We say a network has lost plasticity when its current trained state is less able to learn a new task as compared to a freshly initialized network. So this is like a reference image. If you look at task one, both networks, the freshly initialized network, which is green, and the network orange, which will keep constant in new task, learns this at the same level. But as you move to task two, the performance for the trained network drops, and this trend continues. But if you take a fresh network, it is able to maintain its performance. And this is from the paper Loss of Plasticity in Continual Deep Reinforcement Learning. They performed this experiment using the rainbow algorithm, and it is cycling through different. This is cycling through different Atari games, and then coming back to Alien. So if you use a freshly initialized network, you see that gray curve. You're able to reach the maximum score, and if you use the same algorithm that was trained on different tasks, the performance keeps declining, which shows us that the ability of the neural network to continue learning reduces, which is plasticity loss. These are certain correlates of plasticity. So we know that we are unable to see higher performance, but what is actually happening inside the neural network? These are some of the correlates that we observe frequently. One of them is weight norm growth, which suggests over specialization. The other is increase in the number of dormant neurons. That just means that parts of the neural network have stopped participating. Then we see rank collapse, where representations become less and less diverse as training progresses. And there are changes in the curvature of the loss landscape, which make optimization less effective. Now, some of these mechanisms or some of these, changes in the network, weight growth, dormant units, are kind of benign in stationary settings, but can be pathological under task shift or non-stationary settings. Because in stationary settings, we're kind of expecting it. We are expecting some degree of specialization. The network is adapting to one task, features are task specific, and that is not a problem. But in non-stationary settings, when the same thing happens, when you specialize on task one, and because of which you are reducing the capacity of your network to learn future tasks, that is a problem. Your network is not able to change or like find the new objective, fit to the new objective, and it is no longer able to adapt. Now, this becomes a bigger problem in reinforcement learning, because in reinforcement learning, even when the task itself is stationary, there are sources of non stationarity. The first one is in online reinforcement learning, the agent is collecting its own data. So as the policy changes, the agent starts visiting different states and taking different actions. Basically, the distribution of data keeps shifting over time, and this is what we call the input non-stationarity, the policy changes. The second one is bootstrapping. In many reinforcement learning methods, the agent is using its own predictions about future rewards as the training target. But those predictions are also changing throughout learning. So targets themselves are changing, and that is the output non-stationarity. Together, these two factors means that even a single stationary task in reinforcement learning, the agent needs to constantly adapt to changing inputs and changing targets. Uh, that makes it much harder to preserve plasticity over time, and it amplifies plasticity loss. That is why it is also important to solve this problem in reinforcement learning specifically. All right. So before I move on to the solution, quick recap. We've seen continual learning involves two major failure modes: catastrophic forgetting and plasticity loss. And then we saw that we say a network has lost its plasticity if it is unable to match its performance compared to a freshly initialized network. So here, a natural question is, why don't we just reinitialize a neural network? Because we've seen a freshly initialized network, because of the way we have initialized it. There's decades of research into how to initialize a network so that it can learn and all the signals can flow effectively. Why don't we just keep reinitializing the network? And the problem might be very intuitive. uh, at first, the idea is promising, but the problem is also immediate. Reinitializing the network will wipe out everything that we've already learned. So it might restore plasticity, but it will destroy the stability. And that brings us back to the problem of plasticity stability dilemma. We want to be somewhere, on the Pareto frontier where we are able to balance both these things. This idea has been recently explored in this paper called the primacy bias in deep reinforcement learning. It studied resetting the neural network mid training. So the neural network weights are reset at a fixed interval, but they preserve the replay buffer, so the agent is still able to retain access to past experiences, and that gives it some continuity of information. Resetting helps it recover the lost plasticity. So if you look at this figure, the orange line is the baseline SAC algorithm, and the blue line is where it is where they're resetting the neural network mid training at multiple points. We can see that the overall performance is much higher than the baseline, which shows that resetting is promising. It is able to restore plasticity. But we can also see that every time a reset is performed, there is this drop in performance, which causes instability. Now, this is very harmful. Like, we cannot deploy this because we cannot afford such abrupt changes in performance. So then our work is asking the question, how can we get the benefits of reinitializing a neural network without paying the price in that stability? So let's take a little bit of a detour here. Let's ask, how do humans solve this problem? Because humans are really good at it. We somehow keep learning new things over time while still holding on to old knowledge. And that intuition actually motivates our solution. In the brain, learning and memory are not handled by a single system doing everything at once. Instead, different parts of the brain play different roles. A high level intuition is from the complementary learning systems view. So, hippocampus is associated with rapidly taking in new information. It is good at short term, fast learning. Neocortex is the part that is associated with building more stable, long term knowledge over time. So, one system is more flexible, quick to adapt, while the other is more stable and better at preserving information. And that separation is the key insight. Humans do not rely on a single mechanism to do both these different tasks. So, why are we trying a single neural network to do both of it? That motivated our solution. It's like loosely inspired. Instead of forcing one network to play both roles, why don't we decouple that? AltNet, it's short for alternating network resets. It maintains two networks that periodically switch roles. So as you can see in the figure, there is A1 and A2. These are the two networks. One of them is active, the other is passive. They both have a shared replay buffer. And at any given point, only one network is interacting in the environment, which is the active network. And the passive network is learning off policy from the active agent's experience and the shared replay buffer. At fixed intervals, the active network will be reset, which will restore plasticity, and the passive network, having learned from prior experiences, becomes the new active network. So, what is happening is anytime we will reset the network, we'll make it passive. So, a recently reset network is not allowed to interact in the environment. But that recently reset network becomes passive and in the background continues learning. Because of its restored plasticity, it is able to make better use of the information from the active network and the shared replay buffer. And when it has sufficiently learned, it becomes active again. So this cycle continues, and the alternating structure is able to anchor performance during resets and prevent those performance collapse. Let's see the result. So in this graph, we can see the blue curve is SAC, the orange is standard resets, where you're just using a single neural network and resetting the network mid-training. And the green one is AltNet. So because it is using two networks, we eliminated the drops at the points of reset. Because every time the network got reset, it just became the passive network and the cycle continued. Um, and because now there are no sudden drops in performance, it is possible that this method will enable safe real world deployment. These are more results. This is on DeepMind control suite environments. The red curve in all is SAC, our baseline. The orange curve is the plain resetting. And one note is that everything here is on replay ratio 1, which basically means one gradient update per environment step. This is the hardest setting. And you can notice that the orange curve, which is the standard reset, completely drops its performance because at replay ratio 1, which is the hardest setting, it is not able to quickly recover. In contrast, AltNet, which is the green curve, is competent even at this harder setting. The blue curve here is another method that we compared because it is also a full network reset method. It is resetting with deep ensembles. It uses multiple networks, but the key differentiator is in that networks, any network can act at any point in the environment. Because the way they make decisions is like an ensemble way of making decision. Uh, in contrast, AltNet only allows a stable network to participate in the environment. If a network is recently reset, it is always in the background. We perform the same experiment at a replay ratio 4, and the trend is similar. Like AltNet is more stable and also gives us competent performance. All right, so we address plasticity and stability. Plasticity just means that the network is able to learn more, it is able to better make use of the information. So we found that AltNet also enhances sample efficiency, which is a very critical property for real world domains where data collection is very expensive. So in reinforcement learning, agents are learning by interacting with the environment, and those interactions can be very expensive. So in practice, we do not just want final performance. We ideally also want the agent to learn as much as possible from a few interactions. That is sample efficiency, extracting maximum learning signals from minimum number of interactions. A common way to improve sample efficiency in off-policy RL is to increase the replay ratio, which is the number of gradient updates performed per environment step. The intuition is that, if data collection is expensive, whenever we collect one transition, why not just reuse it more aggressively? Why not like squeeze everything we can out of that sample? And up to a point, it does help. Increasing the replay lets the agent reuse past experiences more extensively and can improve performance. So let's look at the replay ratio 1 to replay ratio 8, this part. We can see that the performance is increasing. It is learning more from same amount of interactions. But this trend does not continue forever. Like when we push the replay ratio all the way up to 32, performance in fact collapses. So more replay is not always better. past a certain point, the agent starts to suffer from repeatedly training on stale experiences. And the more important point is, like, as we are increasing the replay ratio, right, we are also increasing the compute cost, the training cost. So we would want to keep the replay ratio low but achieve maximum performance. Anyways, like, the default assumption that we can always recover more performance by replaying more is flawed. There is a limit, and beyond that limit, performance actually gets worse. This is AltNet at replay ratio 4, which is performing better than SAC, even when SAC uses much higher replay ratios of 4 and 8. AltNet does not need an aggressive replay ratio schedule to achieve that strong performance. It is able to give more value out of each environment interaction at a lower replay ratio. This has two important things, like two insights. First is that AltNet is sample efficient. And second, it is able to achieve that with a lower computational overhead than simply cranking replay higher and higher, right? Okay, so far we've seen AltNet improves plasticity, stability, and sample efficiency. Now let's understand which factors are contributing to its superior performance. And to do that, we systematically evaluate aspects such as model capacity, number of networks, buffer size, and reset duration. So looking at the first hypothesis is that AltNet has increased model capacity because instead of one network, we are using two networks. So we wanted to find out whether any advantages are coming from that increased capacity. Um, in this curve, we see red is the baseline SAC and the green is AltNet with just like all the experiments that I showed you so far with two networks. And in the orange network, we reduce the number of parameters so that it is equal to the number of parameters in baseline SAC, equal to the number of parameters in just one network. And we found that orange network and the green network, which is AltNet at different parameters, they have identical performance. Basically, the advantages are not coming from increased network capacity. Our second hypothesis was that maybe there are certain gains that come from network diversity because, again, instead of one network, we are using two networks. So what if we just increase the number of networks? Can we get additional performance gains? So we scaled it up to 4 networks, and we found that, again, increasing the number of networks does not provide any additional gains. Here, the blue curve is the one with 4 networks, and green is the one with 2 networks. Now that we, eliminated model capacity and the number of networks as the reason for this improved performance, we turn our attention to the defining mechanisms. One is the replay buffer preservation and the periodic alternating resets. So we wanted to see how much does each of this contribute to AltNet superiority. Let's look at replay buffer preservation first. Uh, the replay buffer, as I mentioned, is shared between both the networks and is preserved throughout training. The passive network learns from this buffer, so it has access to the full history of experiences collected by the active network. And up till now, we were using a replay buffer of 1 million. The size was 1 million, so it was able to store 1 million samples. But then we reduced the capacity to 400K samples. So the green curve here is when the replay buffer was completely preserved. And then the gray curve is when we reduce the size of the replay buffer. We can see that a performance gap starts emerging, and it kind of makes an intuitive sense. As we continue resetting, we would need something that is able to still give us information that was collected thus far. And preserving the replay buffer turns out like it is important, and it is one of the reasons we get that superior performance. Now, the second mechanism is the periodic alternating resets. So we decided to stop alternating resets, like we halted the resets after performance plateaued at about like 400,000 steps. So we wanted to see, can we stop the dual network resetting after a point and then just let SAC train the way it does? Because if we were able to do it, we would understand that maybe it is important at the start of the training, and once it has learned enough, it will be able to maintain its performance just using a simple baseline algorithm. But it turns out that is not the case. We see the performance does drop, in fact more significantly than when we don't preserve the replay buffer. And as expected, when we combine both of these things, performance drops even more. So if you halt resets as well as reduce buffer capacity to 400K steps, what happens is that performance declines a lot more. This helped us conclude that it is actually alternating resets that is helping us restore plasticity, and buffer preservation that is helping us maintain continuity of information throughout resets. And I guess we can kind of conclude that plasticity can be lost anytime. Like as training continues, pathologies do get accrued in the network, dormant neurons, weight non-growth, all of this can still accumulate. So it is important that we maintain plasticity throughout training. So far, all the evaluations were in off policy setting with replay buffer. So let's look at on policy reinforcement learning. Let's see whether the benefits can be extended to this setting. Now, first, why is on policy reinforcement learning harder, or why do we care about it, right? So prior methods have failed in this setting. Giuliani and Ash showed in the recent paper that methods that have been tested in off policy setting often fail in this on policy setting. So it is important to just know whether our method perseveres there, or do we need to make any changes. And the difference in on policy setting is that it does not have a replay buffer, or like a big replay buffer to store past interactions. It only learns through freshly collected trajectories. So if we perform a reset here, uh, we cannot be sure how the other network will continue learning. Surprisingly, we find that AltNet is able to give its advantage even in on policy setting. So in this graph, the red one is PPO, which is an on policy algorithm. And then the orange one is the standard resetting. Every time we performed a reset in standard, in just using one network, which was the standard reset, uh, training almost started from scratch, right? Because there is no way to preserve the information that has been learned so far. What changes in AltNet, which is using two networks, is that the passive network is learning from the same trajectories of the active network. So when the active network does get reset, the passive network has been learning from the active network in the background and is able to take over. It is not as stable as the off policy setting, but we do show advantages over the baseline. So we achieved twice of PPO's performance, and we can notice that PPO collapses after it plateaus. Standard resets fail without the buffer. And the reason AltNet, as I mentioned, is able to continue its performance or sustain its advantage in on policy setting is the indirect knowledge transfer that is happening from the two networks and the parallel learning that is able to anchor the performance. So the conclusions are AltNet is able to restore plasticity through the periodic reset. It is able to maintain stable performance, no post reset performance drops through the alternating and the twin network structure, as well as the preservation of the replay buffer. It also has advantages in terms of sample efficiency. It is able to surpass SAC at replay ratio 8 at just replay ratio 4, which means lower computational cost. We also showed how we can be sure that success is being driven by the interplay of the defining mechanisms of AltNet, which is the alternating resets and the replay buffer preservation. It is not due to increased model capacity or network counts. And AltNet works in both settings: off policy, where we tested with SAC, and on policy, where we tested with PPO. It is actually the only full network reset method that is able to do so. Now, future work. Right now, the when we perform resets is actually a predetermined frequency. We just reset at every 200K updates, but ideally, like this would be very different for different environments, and the environment or the agent should somehow be able to trigger that reset, knowing that plasticity has been lost, and also ensuring that the passive network has learned enough to overtake and continue acting in the environment. So exciting future work is definitely like building an adaptive reset scheduling. Then there are also other techniques in this literature that are preserving plasticity and that don't involve a full network reset. So during training, they sometimes get rid of dormant neurons, or there are just so many other interventions. It would be interesting to see how these different interventions can stack up and maybe give even more advantage. There are also future work in the direction of multitask and transfer learning, like extending AltNet to settings where agents face multiple tasks or must transfer knowledge between domains, and alternating mechanism could potentially help with that task and interference. And just to clarify, like we focused on reinforcement learning stationary tasks because, as I mentioned, those stationary tasks also have inherent sources of non-stationarity, but scaling it up to increasing levels of non-stationarity would definitely give us more insights into the capability of altnet and understand more about how plasticity loss and catastrophic forgetting manifest at these varying levels of non-stationarity. All right, so that was my presentation. That was altnet. I am happy to take any questions.
We're still focused on a single task, right?
Yes. So yeah, we focused on single task because it is like the setting where we need to first address this, like solving it in this setting forms the baseline for increasing levels of non-stationarity. But like we do have some preliminary results where we are able to introduce non-stationarity in the environment, like changing the friction of the task. And due to resetting and alternating structure, we are able to see continuation of performance. But in this paper, yes, we only focus on stationary tasks.
Oh, and also you have only one task.
Oh, no.
It's not like a continual, you have a set of tasks
Yeah.
and you, yeah,
Yeah,
it,
we
it
do.
is as, yeah,
Yeah, so we do have one task, and even within that task, because a reinforcement learning agent is slowly collecting its data, so it is slowly learning more about the world, and that is the kind of non-stationarity we deal with. But you're right, it is just a single task.
right. Okay. But typical RL settings are, I mean, of course, those are stationary settings. We assume stationarity. Even though, I mean, you sort of talked about non-stationarity in the context of replay buffers, right?
Yes, like not in the context of replay buffers, but yeah, the
Experience. Yeah.
yes, the distribution changes in terms of the state and actions that are visited. And then the other sources, uh, the target, like the agent is given targets due to bootstrapping, and those evolve as the agent learns more.
Right. Right. Yeah. Okay. Okay. So it can, I mean, like, uh, sort of like it can be extended to a I mean, not multitask. It's like you have a set of tasks, like you have two or three tasks, and then,
Yes,
yeah.
definitely. So the experiment I was mentioning was about like if you have an ant in an environment and you start with a friction of 10 and then you raise it to 20. So that is kind of like non-stationarity in the task. But you're right, like it could also be the agent is learning one Atari game and then it learns another Atari game, and you can just change the task and see how the scales up.
Right. I mean, the and one which mentioned that even though I mean the friction changes, it just the dynamics changes, but the task remains the same, right?
Yes,
So it's a locomotion task.
yes.
So instead, yeah, I mean, how would you evolve? How would you learn one? I mean, one task to a new task is challenging. Yeah.
Right. So my intuition is that because we will, when the task changes, we will reset the neural network at some point. So the new neural network will be able to learn the new task. But I feel like this, it will make remembering the past information harder. Maybe some techniques about varying replay buffers, or some way to differentiate which task the agent is working on might be useful in these settings, but it is a direction for future work.
Right. Okay. Thanks.
Uh, I I was thinking about like, did you notice the wall clock time or the complexity associated with uh, running your algorithm versus others? Like, have you defined that, or is it uh, like, have you analyzed that in any sense?
Right. Yes. So obviously, because we are using two networks and there is twice the amount of learning, our compute is more than a single network. But what what makes this still advantageous is that experiment with sample efficiency. So let's look at replay ratio 8 and alternate at replay ratio 4, right? So replay ratio 8 is SAC. It is doing the same number of updates that alternate is. So here the uh, compute and the time to train would be similar, alternate at 4 and replay ratio 8 at SAC. But we still see that alternate is giving us superior performance. um, does that make sense? Like, even when you maintain the same compute,
Mm-hmm.
you see that alternate will give you more performance. So when you increase replay ratio 8 to 32 or 16, it will be more computationally expensive than alternate at a lower replay ratio.
Mm-hmm. Yeah. Cool. So I was wondering, like, in just a suggestion to have certain metrics or like a wall clock time and a table that represents kind of your analysis to RR8 versus altnet and the rest too. So that would be helpful for practitioners who are wanting to like use your algorithm directly in their code and like try. So that like just a suggestion here.
Yeah, no, definitely. I'll try to include that in the archive version we've posted, because we kind of did it. We just don't have it in the paper right now.
Okay, cool.
I had a doubt. Maybe you had discussed this during the presentation, but one of the limitations you mentioned about the previous work was that loss landscape drastically changes while learning continually, and that causes performance or scalability to drop. So I could not grasp how AltNet actually addresses this limitation.
Yeah, so let me clarify this part. This was kind of the literature review of, sorry, what we see when plasticity is lost. And one of the things that recent literature has noticed, the agent, when the curvature of the loss landscape changes, is unable to learn. Now, this is not related to how AltNet learns. Uh, Let me first tell you why we think AltNet is able to learn. So, in the beginning, the way we initialize a neural network, we try to preserve certain properties during initialization. Now, this has been studied over decades, and I don't know all the details, but like in the beginning, a neural network, because of its initialization, is maximally plastic. Like, if you randomly initialize a neural network, or if you initialize the neural network with all zeros, we know that it is unable to learn. So it is something about having diverse numbers, representations, making sure that signals are able to flow through all these different units that makes initializing a neural network very important for its learning trajectory. Just different initializations can change the path of an agent's learning. Uh, and the reason AltNet is able to restore plasticity is because it restores that initialization. Not the same initialization, it is randomly reinitializing again, but using one of the initialization schemes. So at every point, it like restores its plasticity. Uh, if I talk about the other three, which is like weight norm growth, dormant neurons, rank collapse, all of this, because we reinitialize the neural network, we just solved them. When I talk about the curvature of loss landscape, so there is new literature that actually shows instead of a correlate, it is actually the one defining cause of plasticity loss. Like let's imagine let's imagine a bowl. Let's say in the loss landscape, we only have two parameters for simplicity. And overtraining, because of specialization, the agent finds itself in this landscape where both those directions become flat. Now, when I talk about the stationary task, it is okay to be in this flat region because we have specialized and we are able to perform well on this task. But if you start learning task 2 while you are in this area of loss landscape where these directions are flat, you won't be able, like, you will have no signal or no understanding of where to go. Like, at least that is what I have understood with this changes in the curvature of the loss landscape. But we don't directly base our solution on top of this literature. We think more about what properties we get from initialization and how we can be closer to those properties throughout training.
Yeah, sure, understood. Thank you.
Right. If you don't have any questions, we can wrap up the session
Yeah,
and
thank
thank
you
our
so much.
speaker.
This was really fun. Thanks for inviting me. And if anybody has more follow-up questions or exciting future directions to work on, feel free to email me. I would be very excited to chat. Thank you.
Yeah, thanks, Marcy.
Thank
Thanks
you.
for, thank you.
Thank
Yeah.
you.
Bye-bye.
Bye. Thanks.